Okay, welcome everybody. Today's presentation is by Cameron, who has been working with us over the summer on this bistatic work, and just wrapping it up by presenting it to us and seeing what the results are. I haven't seen all of this, so I'm quite interested to see how he's gone. So, thank you, Cameron.
Okay, so just to start off, encourage questions. It's a little bit of me. I was going to say you can ask as many questions as you want, but if the question, after about 5 questions, I might stop answering them, depending how disruptive they are. Okay, so I've tried to keep things at a fairly low level, though I think everyone here are electrical engineers, or I was going to say, if you've come anyway, you've got some interest in what's going on. So I'm going to start off by quickly going through the theory of what I did, and then I can talk about some experiments I did and what the applications of the experiments were. So, bistatic radar. So normally with radar, what you'll think of is you'll think of something that's like on a warship or air traffic control radar, where the transmitter and the receiver are in the same location. The transmitter sends out pulse, the pulse goes out into space, reflects off targets in space, and then comes back to the receiver, and the receiver's in the same location as the transmitter. Bistatic radar is a bit more interesting because you've got transmitter in one location and a receiver in another, and the difference between the two is roughly on the same order as the difference between the transmitter and the target, or the receiver and the target. So an example of that is chain home, the first system was chain home, which is this system used in Britain in World War II to detect German bombers. AWACS, which is where you've got an airborne control aircraft. So you might have, the RAAF has an aircraft that got a large radar mounted on the top of it, it's a 737. And what happens is that all their fighters can fly about just listening from the pulses from transmitting aircraft, so that obviously as soon as you start using your radar, everyone else can see you, but if you're just listening, no one, it's a lot of people to know that you're there. And the other system is JAWN, which is the air defence radar system to the north of Australia. So what I was going to say, so what I was looking at, however, was bistatic GPS radar, which is what you're doing is using the GPS satellites themselves as illumination sources. And what you're doing is that you're looking for signals that are reflected from the ground when you're in an aircraft or a UAV. So I was going to say that's very, very useful, because then you can have a detector which is low power, it's lightweight, it's passive, and also it's a lot low complexity and low cost than you've got an active system. So essentially you've got the signal coming from the satellite, it's coming down, and with any GPS receiver you'll have a direct signal which comes straight from the satellite to the receiver, and also you'll have a reflector signal which is coming down, it's hitting the ground, and it's bouncing back to your receiver from below to detect your reflection. So very, very quick overview of GPS, which I have to get right with Andrew in the front row. Essentially with GPS, you've got, as soon as you turn on your GPS receiver, what first of all has to happen is acquisition, which is when for each GPS satellite, because the satellites are moving very fast through space and they're moving towards you or moving away from you, and also your receiver's moving, there's going to be a doppler shift that's going to be due to this motion between you and the satellite. When you first turn on your GPS receiver, you don't have any idea what this doppler shift is. So what you've got to do is you've got to work out the doppler shift. And also what happens is that GPS uses CDMA. So essentially you've got a spreading code, which is applied to the GPS signal, and you've got to work out the phase of this spreading code. And that's also, when you first turn on the receiver, this is for each satellite has a different code, this code is unknown, and you've got to try and work out how far through the phase of the code, as well as the doppler shift for each satellite. So essentially the first stage is acquisition, which is where you're trying to work out which satellites you can see, what their doppler shift is, and what their phase shift is. There's tracking, which is once you've found the phase shift and the doppler shift, you'll track that using tracking loops. However, that wasn't something I looked at. And also once you can track, you can decode the messages, which is also something I didn't look at and didn't care about. So essentially with acquisition, you're finding the code shift or phase shift. and you're also finding the doppler shift. So the actual code that's used for spreading is 1023 chips long. So essentially it's just from a statistical point of view, it looks like pseudo-random noise, and it's got two very useful properties, which it's got very good, I think it's very good autocorrelation, so effectively it only correlates with itself one way. The correlation is either very, very high or it's effectively zero. And also, each satellite has a different code and none of the codes correlate with each other. The important thing I was going to say, and also, so what happens is that the satellite transmits code once per millisecond, and the code's transmitted at the bit rate of 1.023 megahertz. So when you actually divide everything out by the speed of light, it turns out that each chip in this code is about 300 meters long. So essentially what you're trying to, when you're doing maybe I'll just go to a diagram, Okay, so with the radar, essentially what's happening is you've got the receiver on a UAV on an aircraft that's flying along, and for each satellite in the sky, there'll be a reflection on the ground somewhere below. And what you're trying to do is you're trying to glean information using remote sensing about the ground below. So for example, the reflectivity of the ground to the L-band radar signal, or you might be trying to work out how far away the ground is below. And for each satellite in the sky, you can see typically one reflection. So as you fly along, what will happen is you'll draw out tracks on the ground below, one for each satellite. So this is for an actual flight from, I think, 2010, where you can see, I think it's 5 reflections on the ground below. And you can actually work out that. From this you can infer the altitude of the aircraft, because when you look, you can see that the aircraft starts descending towards the end because the lines close in on each other, because the distance they are away on the ground from the aircraft is a function of the altitude of the aircraft. So this brings us to delayed Doppler maps. Now essentially what happens is a delayed Doppler map is an array or an image where it's a two-dimensional array and image, and on one axis you'll have the frequency shift or the Doppler shift, and on the other axis you'll have the code shift. And essentially what you're trying to do is you're trying to find the peak. You're trying to find a peak in the delayed Doppler map, which will tell you what the correct phase shift is and what the correct frequency shift is. And essentially what you can do is you can test for each satellite. Each satellite's got its own unique spreading code, and you're checking each spreading code to see if you get a peak in the delayed Doppler map. By testing each satellite in turn, you can work out which satellites are in view, you can work out what their Doppler is, and you can also work out what their code phase is. So essentially what that looks like, if we look at all the possible code shifts, and because the spreading codes are 1023 chips long, there's 1023 different shifts you can try. And also what happens is that because the satellite could be approaching you or it could be flying away from you, there's a shift of about 5 kilohertz you've got to try either side. So if you look here very, very closely, you can actually see the peak delayed Doppler map. And if we go to the next slide, we can actually see that you end up with nice hot spots. That's the direct signal from the satellite, and you can see there's very, very little noise. So where things get really interesting is that the direct signal from the satellite isn't really that interesting. What's more interesting is to do a comparison and to look at the comparison between the direct signal and the reflected signal. Now I've got Zenith and Nadir. So Zenith so this is an actual experiment for an actual aircraft, where the Zenith is the upward-facing antenna on top of the aircraft, and the Nadir is the downward-facing antenna on the bottom of the aircraft. One thing that's important to keep in mind is that GPS signals are right-hand circular polarized, and they tend to, the polarization flips when it hits the target, so you end up with the signal being flipped from right-hand circular polarized to left-hand circular polarized. And from looking at this, what you can see is that the direct signal came in at, say, about 590 code shifts, and the reflector signal came in at 592 code shifts. And before I had each code shift was about 293 meters. So from this, you can see that the reflector signal had to travel about 600 meters further than the direct signal. Because the direct one comes straight from the satellite, and the directed one bounces off the ground and comes to the satellite.
The diagrams you've got there are normalised, right? Because the one on the right is going to be weak.
Yes, that's right. Sorry, you can actually see, that's right, I should have pointed that out, that this has been, they're both normalised. That would actually be a lot weaker. You can actually see that the noise in the background is a lot stronger. Yet normally it's 10 to 20 times weaker, depending on the surface that it's bouncing off. So what you can actually do is you can actually take, for a given frequency, say 3.2 kilohertz, you can take a slice. What you can actually do is you can just take a column from this array and you can go through, and this is when it's been unnormalized, where you can actually see that, I'm not sure if it's the same data, 600. What you can actually do is you can go through and you can see here that the magnitude of the reflected ground signal is delayed and also attenuated as compared to the direct signal from the satellite. So this is useful for two reasons, because what you can do is you can use this to work out the extra path length the reflected signals have to travel, and also you can use this to work out by how much the reflected signal has been attenuated, so that can tell you useful information about the ground below. So one area I went into and was having a good investigation was ray tracing. So essentially what ray tracing is, I've got some diagrams, but essentially what ray tracing, I think it's good to explain quickly. I think it's good to quickly explain while I was having a look at ray tracing. I was doing some modelling of an area. One of the flights was over, there were a number of flights. One of the flights was over way out west, where the ground's very, very flat. It was flying over some lakes. And one of the flights was over Warragam Dam, where you've got ground which the topography is very, very, it's very, very hilly. You've got lots of cliffs, you've got lots of canyons. And I think the lake in this picture is at maybe 200-300 meters high. And some hills go up 600 meters high. So what was very, very interesting here is us looking at the interaction between the signal and the ground, because you can have some interesting effects. For example, you've got the different topography, and in some cases what can happen is that you can have a hill that will come into the way. You can have a hill that will intervene between the signal from the satellite and where you would expect it to reflect from the ground, so you won't be able to see that reflection. Or what can actually happen is that if the ground's facing the right way, for example, to use the extreme situation where if the satellite was directly overhead and the valley was shaped like a parabola and the aircraft was close to the focus, you could have reflections from everywhere. Instead of having a specular reflection from one point, effectively if the aircraft's at the focus of a parabola, you're going to have reflections from everywhere. So that's going to be very confusing if you're trying to use this as an altimeter. So this was, I was doing some research where I was using ray tracing to try and determine what points in the ground would have a line of sight to both the satellite in the sky and also to the aircraft. And also I was having a look at ground interaction between the satellites, but ground interaction between the signal and the aircraft, between the signal, the ground and the aircraft, which, to put it bluntly, is, you can very easily do a PhD on the interactions. I think that I was going to say, what I focused on was specular interactions, which is here, rather than everything else. You can see here it gets very, very complex very quickly. So in terms of practice, the application that I started with is altimetry. So altimetry is where you're getting altimeter is where you're trying to look instead of the range from the satellite, the extra distance the signals travel from the satellite. What you're trying to do is trying to work out the height of the UAV or aircraft above the ground below. So this, I was going to say, because you know the elevation of the satellites in the sky, because you also know where the satellite is in the sky, because you've got GPS receiver, and you know the digital path length, you can work out the height of the aircraft about above the reflection points. So this is where things got very interesting for me, which is essentially what I'm doing is I built an altimeter in software to recreate the flights and recreate the flight and also to try and measure the height, and that worked very effectively. From what I found, it works very, very well above water and not quite so well above land. It's a lot more. I was going to say, to put it quite bluntly, sometimes it works, sometimes it works, sometimes it doesn't, but it works about 95% of the time in the tests I did.
Before you go on from that picture,
Sorry.
you can actually see from that picture what you're talking about. The blue is flat where the water is.
So it's flying over a lake at this point.
And when it starts going up at the end is the land, right? The right-hand end is the land.
Yeah.
And you can actually see that the red estimate starts to get noisier as you get above the land. So you can actually see some nice estimate over the water, less good over the land.
What's the green?
So the green's the actual height of the aircraft, and the red's the So the black is the actual height above sea level of the aircraft.
Yep.
The green is the actual height of the aircraft above the land. So it's basically black minus blue.
Yep.
And the red is what I'm measuring, because the GPS receiver, the actual GPS receiver itself will tell you the height of the geoid. It doesn't know anything about the ground below. So what I'm doing is I'm using as a radar and altimeter where I'm trying to measure the height from the aircraft to the ground below. The thing to keep in mind though is that you're not actually measuring the height of the ground beneath the aircraft. You're measuring the height of the ground at some points away from the aircraft.
Yeah.
So that's one thing you've got to keep in
And the
mind.
offset between the green and the red?
Okay, so this was the height measurement of this is where I'm using the height measurement of the lake was done from the data I've got was from like 1992. So I'm not sure if
I know the answer to the question. I just want you to tell them.
Okay, so from what I worked out from the data, it looks like the lake was lower when we measured it. Well, when it's measured by when I took the measurements from the GPS data, it looks like the lake was a lot lower than when it's originally measured from the data I've got.
So over the lake there's like a constant offset, but over the land you're not getting that offset.
Yeah.
But the thing that's actually interesting is when you actually compare. So that's one of the satellites. At any one time you can set up to say 11 satellites, and they'll be at different elevations, but the best estimates of the height around you will obviously come from the satellites, the highest in the sky. And when you actually compare, say, the 3 highest satellites, the estimates from those tend to be very, very close.
So that's only from one satellite?
That's right, yeah.
Yeah, right.
So this is from a minute of the flight, and what I've actually done is I've broken up the whole flight, which I think goes for maybe 23 minutes or something like that, into 3 separate slides. Now this is why I said about works 95% of the time. The thing to remember is this is from one satellite, so if you've got 3 or 4 satellites which you can actually take measurements from simultaneously and in parallel, then you've got that redundant data, and also you've got an estimate for your location, and if you've got an inertial measurement unit, then you're going to be able to you're going to know that the altitude measurements that you've got there are quite obvious outliers. And I'll actually get to, with the model that I did, I actually get to the reason why I believe that it's lost the plot at that point.
So it sometimes breaks up over smooth surface, but it definitely seems to break up over rough surfaces. So both the hilly bit at the end and the hilly bit over there.
Yeah, that was going to say, that's exactly right. Basically what happens is that in order to be able to compute the altitude, you need to, GPS receiver. The receiver needs to be doing 2 things. Firstly, it needs to be able to detect the signal from the ground below. And obviously if you're flying over something which for whatever reason is not returning or is not reflecting a signal from satellite to receiver, you're not going to be able to compute range measurement. The other thing that can happen is that if the aircraft suddenly starts descending, then what will happen is the distance between you and the satellite up will start increasing. And because the distance between you and the satellite is up increasing, then you'll get Doppler shift because of that. Okay. And what happens is that even though the distance from you to the satellite is increasing, the distance from the satellite to the ground, and then from the ground to the aircraft, is decreasing. So what actually happens is if the aircraft starts to move suddenly, then I was going to say you can have different Doppler shifts for the direct signal from the satellite and the return signal from the ground, which means that you can essentially what I was going to say, which with my implementation algorithm was a fault, which I only realised about three months after I did it. And this is from a second section where you can see it's flying over the lake. It's turning around, it's flying back over the lake. And you can quite clearly see that it tracks very well over the water. It's flying over the lake again, and it's finally coming in to land. So I was going to say, from an altimetry point of view, it seems to be a very interesting application. It seems to work very well. So that's why I thought it was a particularly interesting application. Just from all the work I've done, what happens with the receiver is that when I'm talking about the delay Doppler map, essentially what you're doing is that you'll have some data coming in, you'll be coherently integrating it, and then what happens, just trying to think, I might need to skip over, otherwise, I was going to say if anyone's got any questions, I'll explain at the end, just otherwise I'll be here for 10 minutes.
Yeah, don't explain it.
Don't explain it, okay. Well, basically what I found was that if you're not getting very much signal back from the ground, you can use more data, and that will boost the signal to noise ratio, and then you get signal from the ground.
But that last point's a good one. So the longer you integrate that makes for a longer pixel along the line on the ground. So that your resolution goes down as you integrate for longer.
Yeah, well, I was going to say, essentially it's like with anything where you've got time-frequency trade-off, where the longer the sample you take, the higher the frequency resolution, but the more uncertainty you have about the actual time. And if you use a short integration time, you're very uncertain about the frequency, but you're very sure about the time. And this is what I'm actually showing here, is that you can compare between 10 milliseconds integration time and 10 millisecond integration time and a 20 millisecond integration time. And this is just what I was talking about.
So we'll go back to those two pictures again. What's the conclusion?
Okay, so the important conclusion from this is that you can do two things. If you want to increase the signal, if you want to get better, if you want to increase the signal to noise ratio, there's two things you can do. You can use coherent integration or incoherent integration, and often you'll be using a combination of the two. So coherent integration is, without going into reasons, is advantageous to incoherent integration. The problem is you have to make the assumption that the signal is coherent over time. You're doing the coherent integration. And if you assume that if your assumption is going to be incorrect, then it's actually going to work against you. So what's actually showing here is that 10 milliseconds coherent integration was superior to 20 millisecond coherent integration. Because the surface was rough and the assumption that you could use coherent integration was incorrect, because you won't get coherent signal.
What's that called?
Coherence time.
Coherence time, yeah. So I was going to say in this case the coherence time is probably about 10 milliseconds, but once you got over it, you can actually see this. You can actually see the signal isn't as strong.
Yeah, this is quite an important concept that you're actually showing.
Yeah. So I was going to say, the key thing is there's lots of rules of thumbs, and there's lots of experimentation involved, where you've got to get a good idea of what's actually going on and what actually works. So this is what I was talking about also, where you've got to keep in mind, one thing I've realised that's really important, you've got to keep in mind that you're going to get Doppler shifts as the aircraft moves, the satellite moves, and also, I think most importantly, as the ground underneath the aircraft moves. Because if you've got a reflection from the satellite, which is on the side of the hill, and you're flying towards the, I was going to say.
Oh, no, sorry, I'm just thinking.
Oh, okay,
no,
yeah.
Just stand the other way, yeah.
Sorry, that's what.
Yeah, don't look at me, I'm doing this. I'm thinking. Yeah, keep talking.
Yeah, so what can happen is if you've got an aircraft that's flying along at 50 metres a second, you've got a satellite in the sky, which we'll just assume is good enough as stationary at the moment, because it's so far away, and you've got a hill that's got a 45-degree angle, what's going to happen is the aircraft's flying, if the aircraft's flying along, you're going to have a reflection that's going to run along the ground. As the reflection gets to the hill, it's going to start climbing up the hill. If the hill's got a 45-degree slope, then what's going to happen is that the reflection on the ground is going to suddenly start rising to, from the aircraft's perspective, the reflection on the ground is going to suddenly start rising towards the aircraft. I was going to say, it's going to start rising at 25 metres a second, which means the path length from the satellite to the point on the ground to the aircraft is decreasing by 50 metres a second. I think somewhere in there I'd mentioned there's a rule of thumb. For every metre of second of velocity, that works out to be 5.25 hertz. So all of a sudden you've got 112 hertz difference between what's happening on the aircraft, between the reflection, between the direct signal and the reflected signal. And what that can mean is that if you make the assumption that the Doppler shift is the same for both of them, that all of a sudden you can lose the reflected signal and not be able to see it. The other area which is really interesting, which I didn't go into so much, but I wanted to mention briefly, Andrew, you went into this in more detail, was imaging. So effectively what you can do also is you can look at the return signal power from a point on the ground, and in this case you can see, I think there's 4 or 5 different satellites, and you can look at, I was going to say, you can effectively look at how well the ground's reflecting the GPS satellite at each point, and then you can track this as you go along the ground, and you can use that to actually image the ground and show what's reflecting the L-band signal well, what's not really reflecting it well, and that can tell you useful information. And the good thing about this is that you can have a receiver on a UAV on an aircraft. It's low cost, it's lightweight, it's passive, and also it works day and night through cloud, through fog, through smoke. So obviously there's interesting applications for that, but that's something I didn't go into so much. And that's everything in conclusion. Does anyone have any questions?
Yeah, I got lots. Hey, that was really good, Cameron. That was really interesting. I'm not an electrical engineer, so I'm just struggling to hang on to all the...
Oh, I was going to say I made the wrong assumption.
No, you did a good job though. You did a good job. I was able to keep up with myself.
Well, that's what I hope for.
Yeah, so everyone else is asleep, they're all bored, they've all seen it before. So my question is, I think this is phenomenal that you can... Do you have to do something special with the GPS receiver? Because...
It's not an off-the-shelf GPS receiver.
It'd have to be highly sensitive, surely, because you're basically measuring multipath in a way.
That's essentially what it is that I was going to say, what is other people's multipath is that annoying thing you're trying to get rid of is the crucial thing here that you're measuring.
And so, I guess, do you have any sort of sense of how accurate your final DEM is, digital elevation model, is?
Okay,
just in terms of height.
Okay, so when I was actually doing the numbers, you're looking at maybe 5 metres.
Okay.
I was going to say, the thing that's really important is that there's a number of variables at play. The aircraft what this is mounted on is travelling between 50 metres a second and 70 metres a second. The thing that you can do to increase the accuracy of the measurements in this case is by effectively taking more data for each point on the ground, or taking more measurements from
slowing down,
which obviously the aircraft can't do. Which a UAV, obviously a UAV or something like that can do. So in this case, there would be a trade-off between high accuracy and a long track accuracy.
Yeah. I think you actually asked, you were actually asking how accurate the altimeter is?
Yeah.
Yeah, which is the question you
5 metres.
But the question you actually asked was how accurate is the DEM, which is something he also didn't talk about. So that stuff with the ray tracing, actually, something that Cameron has started looking at, which I don't think anyone's done before also, is looking at the reflectometry and how you may reconstruct. So rather than say use it as an altimeter, say I know my altitude. Where's the land? And so that's what you were doing with the
Yeah.
rate
Well,
tracing.
there's a ton of stuff I wanted to talk about. Unfortunately, I think most people's attention span is about 20 minutes. So
Yeah, but talk about the fancy stuff rather than the easy stuff.
I needed the easy stuff, don't worry. but I mean, this is a pretty amazing application. This is basically you get a sticky UAV out there with a GPS receiver underneath it and do nothing else and you get DEM out of it.
Yeah.
Like you're using,
As long as
you're
it knows
basically scabbing off someone else's signals.
Yeah, so basically the GPS receiver knows its altitude. It knows its XYZ, right?
How much
Because
is
it's a GPS
it?
receiver.
Yeah.
But then you can then reconstruct the land underneath it. And you can reconstruct it at night. And you can
Or
reconstruct
through-
it
or-
without anyone knowing that you're there because it's a passive system. You're not transmitting it.
Yeah.
So how good?
So you can see where that's possibly going.
yeah, so I was going to obviously there's obvious applications in that regard that's completely passive. That we're just talking about before. One application I think would be very interesting is flood mapping. But we're talking the method used at the moment is JAXA. Is that L-band? No. So I think it's longer
And
than
then SAR stuff, yeah.
SAR stuff. Which one method?
LS2.
One method that's used at the moment for flood mapping is obviously if you've got a flood, generally it's because it's raining too much, and the problem if it's raining too much is the ground's all covered by clouds. And one thing that's very important to know is to know exactly where the flood waters are, where they're not, and where they're going. So the one method that was used in the 2010 floods was to actually use satellite-borne radar, because that works at night, that works through clouds, but this also would work at night and also would work through clouds. So I think that's an interesting application
And
as well.
it's really cheap.
Yeah.
It's a GPS receiver.
Yeah.
You can stick it on a cheap UAV.
But the trouble with that is UAV is very limited in range too. You know, like satellite is good because you cover Queensland. Whereas
You see
everything
everything in 10
UAV
minutes,
in Queensland is going to take you 4 months. You know? No, 4 years.
Like how accurately do you need to know the platform's altitude?
Altitude.
Attitude isn't a problem. Position is important. Attitude itself isn't a problem. While
If the platform is wobbling
Well,
away,
the question probably comes down to your attitude may be a bit of an issue if your antenna isn't very isotropic.
that's right. I was going to say it would be a problem if your antenna is perfectly isotropic and you want to use it as an imaging radar where you might want to know, for example, other applications, soil moisture, crop growth, vegetation analysis, all that kind of stuff. But if you want to do something simple like see, is there water there or is there ground there? It's a huge difference between the signal power that you get reflecting off water and you get reflecting off ground.
or just stick in a camera. If you want to see if the ground is there or
Oh, I was going to say that you can do that, but
I
it doesn't
think
work at night and it
this-
doesn't work if there's clouds in the ground, fog in the ground, or...
Yeah, definitely.
How high can you go?
Altitude doesn't matter in terms of you can actually do this from... Within reason, altitude doesn't matter because there's people that are doing this from a satellite where you mount a GPS receiver on a satellite.
Well, and they're actually getting response from a GPS satellite in
Yeah.
space.
Yeah,
So it's
but
going to, when I
this is
say how
Singapore
high, it's
done it,
related to health.
Yeah.
Really?
And when they've been doing it, they've found interferers. Because they've got their antenna looking down. You can see these nice diagrams like that with big nudges across it. Oh, there's an interferer that we flew across in...
We blame the Spanish. Was it in Spain or somewhere? They had to.
The Spanish one is the SMOS. Yeah,
L-band.
Well, what are they doing? Just
well,
sending out some stream of L-band which just interferes with it.
there are radars that are spewing out lots of stuff that's out of band. It's not in the band it should be.
Right.
But also the point to raise that when you've got satellite, you're looking at much larger area and the signal's returning from a much larger area than it's returning from with an aircraft.
Yeah.
Well, obviously, to some degree, you're losing resolution the higher you go up because the spot size on the ground is going to be larger.
Sure. Yeah.
But there's lots of interesting applications, the satellite stuff and also the airborne stuff, which I didn't look at, which is when you're looking at the sea, for example, you can work out sea states. So sea state's basically how rough the sea is, and there's also wind speed estimation, that kind of stuff, which is very interesting.
And that does have a restriction on height. You have to be above a certain height for it to work.
Right.
But I was going to say, if you can imagine if you've got that satellite, I think NASA was a Calypso or something like that, where I think NASA launched some satellites, effectively with GPS receivers, where they want to look at hurricanes, and obviously you can look into the hurricane and you can see what the sea's like, and you can see how rough it is, what the wind speeds are, and obviously it's very useful stuff.
have this idea about the ideal integration time being terrain dependent. Is there any way of...
So you can, obviously you can reverse engineer that, and you can work out how rough the terrain is by looking at trying different integration times. You could use that to, I think where you're going is you could use that to do terrain classification or something. So that's another point, is that you can, you should be able to invert how rough the terrain is by what the maximum coherent integration time is. So effectively with all of this, sometimes it's a bug and sometimes it's a feature with what you're trying to do, and sometimes, it's like with the GPS receiver, I think you can see that the noise in the estimates, the altitude becomes noisy once you fly off the water and onto land. And obviously there's a side effect, but from that you can clearly see on the diagram where's water and where's land.
I've got more questions if
Yeah,
no one
yeah,
else has.
How far did you get with reconstructing the DEM, by the way?
In terms of,
Well, did you reconstruct the DEM from the... Can you do it the other way around, where you were able to say...
not from, I can reconstruct it well when there's only, if I assume the reflections from only one point, that's easy. It's more complex when with the doppler shifts. I haven't done that yet. But obviously that's more complex. So what Andrew's talking about is, what can happen is that you can have multiple reflections from the ground, where you might have a reflection from, you can have multiple reflections from the ground, and the reflections can be different intensities. For example, you might have a reflection from a hillside, and you might have a reflection from water, and the reflection from water will be very, very strong, and it'll be a certain range, and the reflection from the hillside might be a different range, and then you might have a reflection from some terrain that's sloping up that will be a different range and a different Doppler. So what I was looking at was to try and see if you could invert an actual DEM of the ground from this information.
And the shape. So if you get a reflection at a particular delay, the shape that maps out on the ground is an ellipse.
Hyperbola. Was it an ellipse or a hyperbola?
I think if it's something
Side,
of constant length. So if you want to draw an ellipse, right, you can put two pins at the foci, and then have a piece of string and go around like that.
Yeah.
So the length of the string stays the same. That's what I'm thinking. So you've got the satellite and
So effectively you're trying to do SAR with...
there's some sort of your reflection. You know it comes from somewhere on this ellipse.
And then when you take a number of samples, it all adds up.
Yeah, I haven't quite worked out how to do that unambiguously. It would be ellipsoid, I suppose.
Yeah.
There was some ranging stuff that used to happen many years ago, Laura, or something like that, and that was something to do with hyperbole. No,
Yeah.
intersecting
That's time
hyperbole.
difference of arrival.
Yeah, Okay, I've got another question, just because I'm cashing in on the fact that...
Oh, they're good questions, so keep going.
I'm cashing in on the fact that I've got a room full of electrical engineers, and it was really good to hear you talk about the Doppler and the Doppler shift. And I often think about GPS in dynamic applications where you might have it on a car. You might be going quite fast in a car. You might hit a bump in the road or something like that. Do you have any sense of, and this could be two questions, it could be a sense of how well engineered an antenna is, or any sense of what is the minimal amount of Doppler change that will then cause a cycle slip?
Cycle slip.
So here I am.
Ask Eamon after he does the analysis he's doing right now.
So I've got a car, I've got GPS on the roof, I hook into CoreSnet, right? Resolve ambiguities, and I'm getting centimetres.
Yeah.
Start driving, doing 120 down the road, hit a pothole. Do I lose a mile?
The 120 doesn't matter, because the satellite's doing much faster than you are anyway.
Yeah, but
So the Doppler's not the issue. But
but it's the relationship of of how the antenna moves. I suddenly hit a pothole and I
it's
go
called,
dunk, dunk.
that's called jerk, right? So that's the
Okay.
derivative of acceleration. And that's generally the problem. There are two effects that come from jerk. One is the physical movement of the antenna. The other one is the effect of acceleration on the crystal in the receiver. So the crystal actually starts oscillating at a different frequency because it's a piezoelectric device.
Right.
And so both of those things can knock you out. So the analysis that Eamon is doing just works on the antenna bit, not so much on crystal bit, but we are currently looking at the behaviour in high dynamic situations. But the road vehicle application is one of the worst ones because of exactly the problem you're talking about.
Yeah, right. So I wasn't mentioning.
It also depends on the tuning of the loops. So because you've got a surveying grade receiver,
It
the
won't.
bandwidth will be really narrow, so it's easier for it to get knocked out.
Oh, so you can get sort of like navigation grade or something that are
Yeah,
That's right. So if you're prepared to sacrifice your carrier phase accuracy, you might not lose lock.
Yeah, so high dynamics
Right.
receivers don't have the same level of accuracy.
Right,
But
so
they're
what
more
level of
robust.
accuracy might they have? So 5 to 10 centimetres or?
I think you get cycle slip, you get a cycle slip.
Yeah, it'll just be noisy. So it'll be within your 19 centimetres,
Okay.
which is the wavelength.
Yeah.
So it'll be sort of 5
5
centimetres.
centimetres. Okay.
And that ties in with sensitivity as well. So
Yeah. Because I was just thinking about that when you were talking about Cameron, when you were talking about those applications that are dropping, you know, at a certain rate. I was thinking, but it sounds like that. I don't know. It might be a problem for you because
Well, I
it's
think
quite
the more-
dynamic in UAVs.
That's right, but I don't think it's with an aircraft. It's not going to be as dynamic as a pothole because they'll rip the wings off in terms of
Yeah, there is a lot of vibration
yeah.
on a plane.
Our UAV got attacked by a bird.
Yeah.
it might depend on your update rate as well. You're getting 1 hertz signals from your carrier phase. You know, some of the really high-end ones, you get 20 hertz out of them. Yeah.
And that's more of a problem.
Well, you might see things at 20 hertz that
Yeah.
get smoothed over at 1 hertz.
Yes.
Yeah, but we're sort of moving into this high dynamics receiver thing at the moment,
Yeah, right.
and we're probably going to have a lot more to say about it in the near future.
Yes.
What sort of student are you?
Undergraduate.
So it's taster research.
It was sort of a taste of research.
Sort of a taste of
It
research.
just
yeah.
came along after taste of research had already started and asked for
So
something.
now I want to do something.
Yeah.
And
Keep-
you
keep me out of trouble.
money, didn't know what to do with the money.
Yeah, it was very expensive. He did it for the love. Did it for the love of
Good
the
man,
gun.
Cameron. Good man. Terrific.
He's training up to be an academic.
Yeah, I got the t-shirt. I'm in it for the money.
Okay, any more questions? All right, thanks very much.
That was good.